When the cost of the market research was $10,000, we were not willing to conduct the research. So we went with not conducting the research. Now the question is, well, what if that cost of the research could be decreased? If the cost of the research is low enough, maybe we will be willing to conduct the research. So we want to know, what is the maximum Smith should be willing to pay for the market research? Another way of putting it is, what is the expected value of sample information? Expected value of sample information, or EVSI for short, is the difference between the expected value with the sample information and the expected value without the sample information. Here we said free sample information because we don't account for the cost of the information. That is, we don't account for the cost like this. We want the expected value with the information, assuming the information is free. Here, the expected value with the information is what you get if you conduct the research. Without accounting for the cost, the expected value is 84.6. Expected value without the sample information is what you get if you don't conduct the research, so it's 80. The EVSI then is 84.6 minus 80, or 4.6, or dollar amount $4,600. This is the maximum we're willing to pay for the market research. That is the worth of the information. So it makes sense. If the cost is $10,000, we would not want to do that market research. Another question, suppose the market research cost is reduced to less than the EVSI. Remember, the EVSI was $4,600. Then what is the best decision strategy? If the cost is less than $4,600, let's say $4,000 or something, then we would want to do the market research. Let's see what will happen to the tree. This -10 will be changed to, let's say, -4 for 4,000, with the net expected value here now being 80.6. 84.6, minus 4 is 80.6. So this will be 80.6. And that is higher than 80. So now we will conduct the research. And remember, there was an arrow going this way here. And from this node, there was an arrow going this way, the purchase. That's how we got the 68 here. So now the decision will be conduct the research. If the prediction is favorable, then manufacture. If it is unfavorable, then purchase the component. And the maximum expected value from this will be 80.6. An alternative way to present the data on the tree is to start with the net payoffs at the right of the branches. That is, place here the payoffs after subtracting the cost of the market research, instead of having to remember the cost here. That means 200 will become now 190, and 60 will become 50, and -30 minus 10 is -40, and 130, 70, and 10. And same thing here. Then what happens is, as you can see, the expected values at the nodes now are 10 less than before. So like this one used to be 109.5, now it's 99.5. Then this one used to be 98, now it's 88. And that change propagates through all the nodes where the market research is conducted. So now we don't have to account for the cost here, since it was already accounted for at the beginning here. So we could just delete that cost. And now we just do a straight comparison between nodes 2 and 3 to decide on whether to do the research. So here we would say, okay, here's the net expected value from conducting the research 74.6, and that's less than 80, so we would choose not to conduct the research. Same as before. I'd like to show you another variation. What if there were a third alternative of doing nothing that has a payoff of 0? How would this change the optimal decision strategy? Here's a new payoff table with the 3 alternatives: manufacture, purchase, or do nothing. Well, do nothing might mean that we might not get this new component at all, maybe because we decide not to sell the product that uses this component, so the payoff is 0 regardless of the demand level for the product. For the decision nodes 3, 4, and 5, we will need a third branch for doing nothing. Now, when you do nothing, the demand level, high, medium, or low, is no longer relevant because the payoff is 0 regardless of the demand level. So you don't need to draw the branches for all these 3 demand levels here. So you could just have one branch like this and with a payoff of 0. Now, when you choose a node value at one of these decision nodes, we need to include a third branch in the comparison. Now here, what is the highest value for the decision node here? Well, 109.5, 98.0. So that doesn't change the node value at 4. And similarly, at node 5, it will still be 68. And at node 3, the value will still be 80. So 0 from doing nothing will not be the highest value in any of these decision situations. So the optimal decision strategy will remain the same. But just as a hypothetical illustration, suppose the values at nodes 10 and 11 both happen to be negative. Negative 52 and negative 68 here. In this case, comparing these 3 values, negative, negative, and 0, now 0 will be the highest value. So now then this value will be changed to 0 from choosing doing nothing, and this result will propagate to the rest of the tree.